A black hole is not a place where things simply disappear. It is a boundary where our familiar rules begin to soften, where gravity becomes so intense that space itself bends inward, and where time slows toward a whisper. As you breathe right now, somewhere in the distant darkness of the universe, entire stars are being stretched into thin streams of light, pulled toward an edge that no spacecraft, no signal, no particle can ever return from. And yet, behind that quiet horizon lies one of the most profound questions in physics: what exists on the other side? Einstein once hinted that a black hole might not be an ending at all, but a passage, an idea long overshadowed, then slowly rediscovered. Whether this boundary hides a bridge, a mirror, or simply the final limits of our understanding, it remains one of the deepest mysteries we can contemplate in the dark. If this calm journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps this quiet corner of the universe stay alive. Now we drift into the first part of our exploration. Part 1. What truly happens at a black hole's edge? The edge of a black hole is not a surface. It has no texture, no glow, no barrier you could ever touch. It is simply the point where light can no longer climb outward. Physicists call it the event horizon, a silent threshold where time for you and time for the universe begin to disagree. As you drift closer, distances stretch, clocks distort, and the rules that shaped your entire life begin to fold into something new. Even from far away, the horizon exerts a quiet influence. The gravity surrounding a black hole isn't a pulling force in the ordinary sense. It is the curvature of space itself, bending the very path that matter and light must follow. As you approach, straight lines turn into arcs and arcs become spirals. You are not dragged inward. You glide, following the natural flow of a warped geometry. Space does not feel hostile. It simply narrows your choices, guiding every path toward the same inevitable boundary. To understand how strange this edge truly is, imagine shining a flashlight upward while standing on Earth. The beam escapes easily. Now, imagine shining that same beam near a black hole. Gravity steals a little more of its energy, stretching its light into redder wavelengths. The closer you move, the more the beam struggles, its color drifting toward infrared, then toward microwaves, then toward frequencies so long they slip beyond what any human instrument could detect. At the horizon, even a beam of light pointed outward has no strength left to rise. It simply hovers, frozen in place, as time stretches it toward infinity. This gravitational redshift is one of the clearest signals that you are nearing something unlike any other region of the cosmos. It is the universe whispering that its usual rules are beginning to strain. From your perspective, the world still feels stable. Your heartbeat is steady, your thoughts flow smoothly. But to a distant observer watching your descent, everything slows, not because you slow, but because their version of time is being warped by the gravity surrounding you. This disagreement between perspectives is not an illusion. It is a physical effect predicted by general relativity, confirmed through decades of observations. Near massive objects, time runs differently. Clocks tick more slowly. Signals stretch. Motion softens. GPS satellites orbiting Earth must correct for this difference every day, because their clocks high above the planet run faster than the clocks on the ground. Near the horizon of a black hole, this difference becomes extreme. A few seconds for you could mean minutes, hours, or even years for someone observing from afar. If you could look back during your fall, you might see the universe behaving in ways that feel impossible. Colors shift. Light bends around the black hole in elegant loops, forming arcs known as Einstein rings. Behind you, the region of sky directly opposite the black hole may appear magnified or repeated. The gravity is so strong that it can fold distant starlight into multiple images, overlapping them like reflections on a warped sheet of glass. This bending of light creates what astronomers call the photon sphere, a delicate boundary slightly outside the event horizon where light can orbit the black hole in perfect circles. It is not a stable orbit. A single disturbance, even the faintest push, sends photons spiraling inward or flinging outward. But for a moment, they trace loops through a region where space itself seems to hesitate between falling and escaping. If you pass through this sphere, you would see light rush past you in streams, swirling around the black hole like a river of fire. Yet for all this visual drama, the horizon itself remains silent. There is no sign you are crossing anything significant, no sudden drop, no shift in pressure, nothing to hint that the rules of reality have just changed. General relativity predicts that your passage through the horizon feels smooth. This is called the equivalence principle, the idea that, locally, gravity is indistinguishable from simple motion. Falling into a black hole is not like crashing into a wall. It is like drifting through the calmest ocean current you have ever known. The strangeness arises only when you try to compare your experience with someone else's. To observers far away, you appear to slow, then freeze just above the horizon. Your signals grow fainter. Light from your body stretches until it slips into darkness. To them, you never quite cross the boundary. You simply fade, becoming a ghost of red-shifted photons lingering at the edge of oblivion. But your perspective, the local perspective, tells an entirely different story. You continue inward with no obstacle at all. The universe outside accelerates wildly, stars drifting into streaks of light as time distorts around you. The horizon opens like a doorway into deeper curvature, where the usual notion of distance begins to unravel. Inside, space and time trade roles. Movement toward the center becomes as inevitable as the flow of time itself. You cannot turn around, because there is no longer a somewhere else to turn toward. All paths lead inward. This is not a choice or a force. It is geometry directing every possible motion toward a single point. This point, the classical singularity, is where Einstein's equations predict that curvature becomes infinite. But most physicists believe this is where general relativity reaches its limit, not where reality stops. Quantum theory suggests that spacetime might resist infinite compression, forming instead a region of extreme but finite density, a place where new physics takes over, waiting for a theory that unites gravity and quantum mechanics into a single description. Long before you reach that center, though, space becomes so curved that the meaning of direction itself blurs. The radial coordinate, your distance from the center, behaves less like a physical distance and more like a measure of inevitability. The closer you move inward, the faster inward becomes. It is not motion anymore, it is structure. If you could hold a clock in your hand, it would continue ticking normally by your own measure, but nothing outside the horizon would ever see those ticks. Your time becomes isolated, sealed beyond the reach of the rest of the universe. What happens to that time, what becomes of the information it contains, is one of the deepest questions in theoretical physics. Some models suggest the information remains encoded in the horizon itself, woven into subtle vibrations of spacetime. Others propose that the interior avoids collapse through quantum effects, forming a tunnel that leads elsewhere. Still others imagine the interior like a hidden pocket of spacetime, cut off from the rest, where the laws we know soften into something unfamiliar. But at the horizon itself, at this quiet boundary where light surrenders, the truth is deceptively simple. Nothing pushes you back, nothing warns you. The edge is not an ending, but a place where perspectives diverge, where the universe reveals that its laws are broader and deeper than our everyday experience can sense. As you continue this quiet descent, one question lingers, soft but persistent. If the horizon changes time, then what happens to time just inside it? Part 2. Why does time slow down near a black hole? Time near a black hole doesn't flow the way it does here. Gravity bends the fabric of spacetime, stretching seconds into minutes, minutes into hours. To a distant observer, anything falling toward the horizon appears to freeze in place, trapped in a moment that never ends. Yet, for the falling object itself, time feels natural, steady, almost ordinary, until it doesn't. The effect is not symbolic. It is not poetic or exaggerated. It is a measurable, testable distortion predicted by Einstein's general theory of relativity. According to that theory, time passes differently depending on where you are and how strongly gravity presses against the fabric of spacetime around you. Earth's gravity causes this subtle slowing, too, so subtle that you would never notice it, but satellites in orbit feel a slightly weaker gravitational pull than clocks on the ground, and their time runs faster by a few billionths of a second each day. We correct for this difference constantly because without it, GPS navigation would drift by kilometers every 24 hours. Near a black hole, this same effect becomes enormous. Gravity there does more than bend time. It stretches it almost beyond recognition. To understand why, imagine placing two identical clocks in the universe. One sits far from any massive object. The second is slowly lowered toward a black hole. From the perspective of the distant clock, the clock near the black hole begins to tick more slowly. Its seconds lengthen, its rhythm softens, it records fewer moments than the clock far away. This isn't a trick of perspective, it's built into the geometry of spacetime itself. In relativity, mass curves spacetime, and time runs slower in regions where curvature is intense. A black hole's enormous density creates a well so deep that near the horizon, time is stretched almost to infinity. If you were hovering safely near the horizon, not falling, just hovering with powerful engines, you would feel this difference in your bones without realizing it. You'd age at a slower rate than anyone who remained far outside. A minute for you might be an hour for them. A year outside might pass as a day where you are. The closer you hover, the more dramatic the effect becomes, until 1 second for you corresponds to years, centuries, or even millennia of the universe outside. This phenomenon is known as gravitational time dilation, and it is one of the most profound insights relativity has ever given us. But for the person falling in, something else happens. The slowing of time does not occur in their own experience. Their heartbeat feels the same. Their thoughts flow the same. They drift inward with the gentle, steady passage of their own time. The distortion exists only in comparison, only when you view one frame of reference from another. This is the heart of relativity. Time is not universal. It is local. Every object carries its own clock, ticking according to the gravity and motion it experiences. When you fall through the horizon, your clock doesn't slow down from your point of view, but everything outside seems to race ahead. Galaxies blur, stars drift into rapid motion. The universe appears to accelerate, as if the outside world is being pushed forward while you sink into a deeper well. This disagreement is not a contradiction. It's the very structure of space-time flexing under extreme gravity. To a distant observer, you never truly fall through the horizon. Instead, you freeze just above it, becoming dimmer and redder as your signals stretch into lower frequencies. Eventually, your image fades into darkness. But from your perspective, you cross the horizon without hesitation. There is no jolt, no barrier, no sense that you've passed something special. The contradiction arises because time for you and time for the universe outside have diverged completely. The reason lies in the nature of light. Information travels through the universe carried by photons. Those photons must climb out of the gravitational well to reach a distant observer, and as they climb, they lose energy. Their wavelengths stretch, their arrival rate slows. The outside observer sees fewer and fewer signals from you, spaced farther apart, as if time itself were dissolving. This slowing reaches its limit at the horizon. No signal can escape, no photon can rise. The outside universe sees your final moment stretched out indefinitely. This is why, in some descriptions, an object falling into a black hole appears to experience infinite time passing outside. The falling object does not witness this infinity because its own time continues normally. But others, far away, would see the universe evolve for as long as the black hole exists before the object ever seems to reach the edge. Think of it like two readers holding the same book, but with different lighting. One reader can see every page clearly, turning them at a steady rhythm. The other sees the pages only when faint hints of light manage to reach them, each page stretched, distorted, arriving later than the last. Both read the same story, but their experience of its pace diverges. In the case of a black hole, this difference becomes cosmically large. Time dilation is not just a change in speed, it becomes a separation of realities. This slowing also explains why black holes preserve information on their horizons. If anything falling in appears to freeze from the outside, then its last visible state is smeared across the edge of the horizon. This concept inspired physicists to propose the holographic principle, the idea that the information inside a region of space may be encoded on its boundary. Time dilation is not the reason for the principle, but it creates the visual metaphor that helped some of the greatest minds imagine it. Einstein once noted that the difference between gravitational time dilation and special relativity is subtle but crucial. Acceleration and gravity are interchangeable in the mathematics of relativity. Standing on Earth, you feel a downward force, not because gravity pulls you, but because the ground holds you up, resisting your natural curved path through spacetime. In orbit, astronauts feel weightless, not because gravity vanishes, but because they follow that natural path without resistance. Near a black hole, that curved path becomes far more dramatic. The deeper the curve, the slower time flows. Time dilation is not caused by force, it is caused by geometry. If you could see spacetime as a landscape, it would resemble a massive bottomless funnel, narrowing toward the center. The closer you get to the bottom, the more stretched each layer becomes, like rings pulled farther apart. Time flows along those layers. Near the top, it moves quickly. Near the bottom, slowly. At the horizon, the stretching becomes infinite. This picture, simple as it is, captures the essence of why time near a black hole does not behave like time elsewhere. To the falling traveler, this stretching remains invisible, but the outside universe speeds ahead. If you fell into a supermassive black hole, you might watch billions of years of cosmic evolution unfold in a brief, accelerated blur just outside the horizon. Stars explode, galaxies collide, light redshifts into darkness, and then, once inside, even this accelerated view fades, and only the inward flow remains. There is something quietly humbling about this effect. Time is not a universal beat, not a cosmic metronome ticking identically everywhere. It is flexible, elastic, shaped by mass and motion. In the gentle regions of space, the differences are tiny. Near a black hole, they become profound reminders that our understanding of reality depends entirely on where we stand. And as we continue this slow descent into the physics of black holes, another question naturally emerges. If gravity can stretch time, what happens when gravity becomes strong enough to distort space itself beyond recognition? Part 3. What does an event horizon look like up close? If you could float near the horizon safely, you would see something strange. Not a wall of darkness, but a sphere of light swirling around you. Photons trapped in orbit form what physicists call the photon sphere, a glowing halo created by gravity so strong it bends light around itself. The sight would be unlike anything else in the universe. From a distance, a black hole looks simple, an absence, a shadow stamped onto the fabric of the cosmos. But as you drift closer, the simplicity dissolves. The horizon that appears solid from afar becomes a shifting, fluid boundary where light behaves in ways your intuition has never prepared you to understand. Instead of darkness, you are surrounded by motion, streams of light looping, twisting, and folding upon themselves in a quiet ballet shaped not by matter, but by pure geometry. The first thing you notice is how the background sky distorts. Stars behind you seem to slide across the black hole's face, stretched into arcs, then pulled into narrow crescents as their light bends around the gravity well. The constellations you once knew begin to blur, their familiar shapes breaking apart as light follows curves that no straight line can explain. It is not chaotic. The motion is steady and smooth, but it is unlike anything the human eye has ever evolved to see. Move a little closer, and the distortions intensify. The black hole swells in. Your vision, not because it grows, but because space itself funnels toward it. Around its edge, a shimmering ring ignites, the photon ring, the place where light circles the horizon many times before either escaping outward or spiraling inward. This ring does not flicker or pulse. It remains steady, as though carved into space-time itself, always present no matter how you move around it. This glowing rim is not merely a visual effect. It is the last stable orbit for light, hovering at radius 1.5 times the Schwarzschild radius for a non-rotating black hole. Any closer, and light cannot maintain an orbit, it spirals inevitably inward. Any farther, and it swings around and escapes. What you see is not one loop of light, but the superposition of countless paths, photons that have circled once, twice, dozens of times before the geometry finally decides their fate. Because light from all directions bends around this region, the photon sphere acts like a lens. If you looked closely, you would see the universe repeated again and again in concentric layers. Distant galaxies appear mirrored, shrunk, then folded into themselves. The black hole becomes a cosmic hall of mirrors, reflecting the universe not with glass but with gravity. If the black hole is rotating, the sight becomes even stranger. A rotating black hole drags space-time around with it, a phenomenon known as frame dragging. Near such a horizon, everything, including light, must rotate in the direction of the spin. The photon sphere becomes asymmetric, brighter on the side where rotation adds to the speed of orbiting photons, dimmer where it subtracts. The ring appears lopsided, one side glowing intensely, the other softened into a shadowed arc. This asymmetry is the signature of spin, a cosmic fingerprint. The Event Horizon Telescope captured a glimpse of this structure in 2019 when it imaged the supermassive black hole in galaxy M87. That orange ring, blurred by immense distance, was a real photograph of this photon sphere. But seen up close, it would not look blurred. It would be sharp, luminous, and impossibly intricate, a perfect circle of trapped starlight swirling around the darkness. As you approach the photon sphere, the surrounding environment becomes increasingly surreal. Light from behind you bends so sharply that you begin to see your own reflection, not a true reflection, but an image formed by light looping around the hole and returning to your eyes. You see yourself floating in the sky ahead of you, distorted and delayed by the time it took the photons to complete their orbit. You are observing a moment of yourself from the past, carried by the curvature of space-time. This effect grows more pronounced the closer you get. Move slightly, and your ghost image lags behind, like a memory stitched into the space before you. It is not your shadow, but the imprint of your own path through space-time, bent back toward you by gravity. Look upward, away from the black hole, and the universe appears to shrink into a cone. The sky above becomes a circular window into the cosmos, while everything around you stretches toward the horizon. Space seems to tilt. Straight lines fail. It becomes difficult to judge distance because distance itself no longer follows Euclidean rules. You might reach out your hand and feel as if you could almost touch the place where light circles endlessly, even though vast stretches of warped space separate you. The horizon below remains dark, but not featureless. It is not a surface, no reflection, no texture, yet it behaves like a boundary nonetheless, a place from which no information returns. You might feel drawn to describe it as a sphere of absence, but even absence feels too solid a word. Instead, the horizon resembles a window into non-existence, a place where pathways vanish and time ceases to cooperate with the universe outside. And yet, despite this strangeness, your surroundings feel calm. Gravity changes dramatically near the horizon, but not in the violent way fiction often imagines. If the black hole is supermassive, millions of times the mass of the sun, the tidal forces at the horizon are gentle. Stretching or compression is minimal. You could drift through this region without any physical sensation of danger. The danger is not in your body's experience, but in the geometry you are about to cross, one that isolates you from the rest of the universe forever. Just above the horizon, the photon sphere glows steadily, but the closer you drift, the more the sight around you changes. The ring seems to rise, curving upward as the laws of perspective invert. Eventually, it climbs above your field of view until it forms a warped halo circling the entire sky. This is not the photon sphere moving, it is space folding inward around you, turning the structure of angles and directions inside out. If you stopped your descent at the perfect spot, you would witness a cosmic illusion, the universe above, the photon sphere around, and the horizon below, all merging into a single continuous panorama. You would see the cosmos reflected through the black hole's gravitational lens, creating layers of images stacked upon one another like ripples in a pond. Each layer would represent light that has taken a different path, some direct, some looping once, some looping twice or more before reaching your eyes. If you watched long enough, you might see distant stars drift into the ring, circle it several times, and then fling outward again, distorted but recognizable. The photon sphere is not static. It is dynamic, constantly fed by light from the outside universe. It glows because the cosmos itself illuminates it, and then, just below it, the horizon waits, silent, unlit, indifferent. As you study this glowing architecture of warped space-time, a natural question rises gently from within the awe. If light behaves this strangely near the horizon, what happens to time and space once you cross it? Part 4. What happens to light that tries to escape? Light near a black hole loses energy as it climbs away, stretching into redder and redder wavelengths. Close enough to the horizon, it stretches infinitely, fading into darkness. This redshift isn't just a visual effect. It is a sign that even light is being slowed, bent, and drained of its usual certainty. To understand what this means, imagine a single photon, one tiny packet of energy, leaving the surface of a distant star. In empty space, it travels freely, losing no energy, its wavelength unchanging across the vacuum. But near a black hole, that simple picture breaks apart. Space-time curves inward, and the photon must climb out of a gravitational well far deeper than anything found in ordinary cosmic environments. The climb costs energy. And for light, the only way to lose energy is to change wavelength. The closer the photon is to the horizon, the more dramatic the shift becomes. A wave once glowing blue becomes green, then red, then infrared, then microwave. The peaks stretch farther and farther apart, as though gravity is pulled on the wave itself. Eventually, the wavelength becomes so long that the photon drifts beyond the reach of any detector we could build. No telescope, no antenna, no instrument can capture a signal that has been stretched toward infinity. The photon still exists, it hasn't vanished, but to the outside universe, it has faded into silence. This process, called gravitational redshift, is not just a prediction of general relativity. It has been measured repeatedly. In 1960, the Pound-Rebka experiment detected gravitational redshift using gamma rays in a Harvard University physics tower. In 1976, a rocket-borne experiment called Gravity Probe A measured the effect with extraordinary precision. Today, GPS systems must continuously correct for gravitational variations in time and frequency. What we see near a black hole is a familiar effect pushed to its most extreme limit. But near the horizon, redshift becomes more than a shift of color. It becomes a boundary between two versions of reality. From far away, no light can escape the horizon, not because the black hole absorbs it, but because the stretching becomes infinite. Light slows, softens, and fades until it can no longer communicate any information outward. It is as if gravity steals the photon's ability to speak. If you could hover just outside the horizon, you would witness something profound. Light emitted outward from matter falling in would appear weaker, dimmer, and redder with every meter of descent. A glowing star plunging toward the black hole might start out brilliant, then fade to an ember, then to a phantom glow, and finally to nothing at all. By the time it reaches the edge, its light no longer carries energy in any meaningful sense. It becomes stretched across time itself. This fading is not because the black hole is eating the light. It is because the structure of space-time is so curved that the photon must give up more and more of its identity in order to rise away from the horizon. In a way, the photon becomes thin, drawn across an ever-expanding wavelength until it dissolves into the fabric of time. To the falling object, none of this feels unusual. Light emitted inward or sideways looks normal. Even photons emitted upward appear ordinary at the moment of emission. But as they travel outward, the geometry of spacetime shifts beneath them, stretching their wavelengths far beyond recognition. This is the strange duality of relativity near a black hole. For the emitter, nothing is wrong. For the distant observer, everything is changed. The slowing of light, the stretching of its wavelength, and the fading into darkness are all signs that time itself is being distorted. A photon encodes the frequency of an emitter's clock. When the photon slows and stretches, it is telling the outside universe that the clock of the falling object is ticking more slowly. Redshift, then, is not just a property of light, it is a fingerprint of time dilation. If you could watch a series of pulses being emitted by a beacon falling into a black hole, you would see something remarkable. The pulses would arrive slower and slower. Each new flash would be weaker and more spread out than the last. Eventually, the signals would seem to stop altogether, even though the beacon continues to function normally from its own perspective. The outside universe sees the beacon freeze at the horizon, its last signal stretched across eternity. This frozen image is one of the strangest implications of relativity. Nothing truly stops at the horizon from its own point of view, but from outside, it appears trapped forever in a single moment. Even light seems unable to break free from this gravitational illusion. The very concept of escape becomes ambiguous. A photon trying to climb outward must navigate not only distance, but the shape of spacetime itself. If spacetime curves downward faster than the photon can climb upward, the photon is lost. It follows the path dictated by geometry, not by force, and that geometry leads inward. Inside the horizon, things become even more dramatic. A photon emitted upward cannot move outward at all, because outward no longer exists as a permissible path. The photon moves inward not because it is pulled, but because the light cone, the region of spacetime that defines all possible paths, tilts so sharply downward that every possible route leads deeper toward the singularity. The phrase, "nothing can escape," is often misunderstood. It does not describe a force pulling things inward, but a reshaping of spacetime so complete that escape paths simply cease to exist. But the story of light near a black hole does not end with escape or collapse. There is another layer, one that leads modern physics into some of its most difficult questions. Stephen Hawking discovered that black holes are not entirely black. Quantum effects near the horizon cause pairs of virtual particles to flicker into existence. Normally, these pairs annihilate instantly, but near the horizon, one particle can fall inward while the other escapes outward as a real particle. This process creates Hawking radiation, a faint glow emitted by black holes over unimaginable timescales. The escaping particle carries away energy, meaning the black hole loses mass very slowly. Over trillions upon trillions of years, a black hole could evaporate completely, leaving behind only radiation. Light near a black hole, then, behaves in two contradictory ways. It is trapped by gravity's curvature, yet it can also emerge through quantum effects that bypass classical rules. This tension between general relativity and quantum mechanics lies at the heart of the black hole information paradox. Some physicists argue that the redshift stretching of light is evidence that information from inside must be encoded on the horizon. Others argue that Hawking radiation itself must carry information outward. Still others propose that new physics arises at the horizon, firewalls, quantum chaos, or holographic surfaces that rewrite the rules of spacetime. But regardless of these frontiers, the behavior of light remains the simplest, most direct clue we have. Gravity steals its energy, stretches its wavelength, and reveals the slow unraveling of time as it climbs outward. To stand near a black hole, to witness light bending, fading, and stretching into near eternity, is to realize something profound. Light is not the universal constant we imagined. It is a traveler whose journey depends entirely on the shape of spacetime. And as this quiet truth settles, another question rises softly. If light cannot escape freely, what becomes of the matter that falls inside? Part 5. Does anything survive crossing the horizon? Crossing the horizon is not an explosion or a violent snap. It is quiet, smooth, uneventful. General relativity predicts that an object falling in would feel nothing at the exact moment it crosses the threshold. No sign, no warning. Just a one-way drift into deeper curvature where the meaning of direction slowly dissolves. In many ways, this is the most counterintuitive truth about black holes. Popular imagination paints them as cosmic shredders, violent, tearing, catastrophic. And while tidal forces can be lethal, especially near small black holes, the horizon itself is calm. It is a place where nothing dramatic occurs locally, even though everything dramatic is occurring globally. To the falling traveler, the journey through the horizon feels natural, uneventful, as if the universe has quietly opened a door rather than slammed one shut. This paradox lies in the way relativity divides experience into two perspectives: what you feel in your own frame of reference and what the universe outside sees. For you, crossing the horizon is indistinguishable from floating through any other point in spacetime. For an idle observer watching from afar, you never truly cross it. Instead, you appear to slow down, dim, redden, and freeze just above the boundary, your signals stretched across time until they fade into silence. But your own reality, your proper time, continues unhindered. General relativity insists that nothing special happens locally at the horizon of a sufficiently large black hole. No sudden acceleration, no crushing pressure, no physical barrier. You simply drift deeper into the curvature of space-time. That is the key. The horizon is not a place, but a condition. It marks the point where all paths lead inward, not because a force pulls you, but because geometry leaves no other option. Imagine walking across a frozen lake. The ice stretches out smoothly beneath you, unbroken, featureless. Yet somewhere beneath the surface lies the thinning region where the ice can no longer support weight. There is no visible marker, no line, no boundary. Just a deeper structural truth that only becomes apparent when you cross it. The event horizon is similar, though instead of thin ice, it marks the limit of escape. You don't fall through a membrane. You pass into a region where light itself can no longer point the way back. So the question becomes, what survives this crossing? If the black hole is supermassive, almost everything does, at least initially. The tidal forces at the horizon of a huge black hole are gentle. Gravity pulls you inward, but not violently. For a black hole millions of times the mass of the sun, you could cross the horizon without a single atom in your body noticing anything unusual. Not your eyes, not your skin, not the cells quietly dividing inside you. From a sensory perspective, it might feel like gliding into shadow, but the shadow offers no resistance. This survival is temporary, however. The deeper you move inward, the stronger the curvature becomes. Eventually, tidal forces will grow, stretching and squeezing along different directions. But the horizon itself is not where this harsh reality is felt. The horizon is simply the point beyond which your future inevitably leads toward the center. To understand why survival is even possible, we must recall how relativity treats motion. Gravity is not a force, it is the natural path an object follows when it is not being forced at all. Inside a black hole, falling inward is not an accelerated motion, it is free motion. You are not being crushed by gravity, you are flowing along the shape of space-time. But this gentle descent hides something profound. Even though you feel nothing at the horizon, your fate has changed. Before crossing, there existed paths, trajectories through space-time that could carry you outward again. After crossing, none of those paths exist. The inward direction becomes temporal rather than spatial. Moving deeper becomes as inevitable as moving forward in time. So, does anything truly survive the crossing? Locally, yes. Globally, no. It is survival of continuity, not survival of freedom. Take a simple photon emitted near the horizon. From the outside, that photon appears to redshift until its energy vanishes. From your perspective inside, the photon behaves normally, carrying light and information as though nothing has changed. It still illuminates your surroundings, it still reflects off surfaces, but this light can no longer reach the outside universe. Its future lies entirely inward, just as yours now does. In this sense, crossing the horizon severs not your existence but your relationship with the outer cosmos. To any observer still outside, you have become a fading imprint, an image stretched across the horizon, red-shifted into invisibility. To yourself, you continue forward without interruption. Both descriptions are correct. Both realities coexist. This is the strange duality of relativity at the horizon. Matter falling into a black hole also survives the crossing at first. Atoms remain intact. Molecules remain intact. Even complex structures like cells or spacecraft remain intact for a time. Astrophysical simulations show that infalling material maintains its structure well past the horizon in supermassive black holes. The real destruction occurs deeper in, near the region where curvature grows uncontrollably and tidal forces become overwhelming. The exact nature of this inner region remains uncertain. Classical relativity predicts a singularity, a point where density becomes infinite and the curvature of spacetime diverges. But infinities in physics usually signal a theory's limitation, not nature's truth. Many physicists expect that quantum gravity, an as-yet undeveloped theory that unites quantum mechanics with relativity, will replace the singularity with something finite, a region where spacetime is compressed but not infinitely so. If such a theory is correct, then matter might not be destroyed in the traditional sense. Instead, it may be transformed, compressed into a state we have no language for yet, governed by laws we haven't discovered. Does anything survive in a recognizable form? Likely not for long. But survival in physics is less about identity and more about information. And here, the black hole presents its greatest mystery. According to quantum theory, information cannot be destroyed. Yet, classical relativity suggests that anything crossing the horizon is lost forever. This conflict is the heart of the black hole information paradox, a puzzle that has shaped decades of research. Some theories propose that the information of everything falling in is stored on the horizon itself, encoded in microscopic degrees of freedom. Others propose that information escapes slowly through Hawking radiation. Still others suggest that spacetime reorganizes information in ways we do not yet understand. But regardless of which theory proves correct, one truth remains. The crossing is gentle, even if the consequences are profound. As you descend past the Aeton horizon, the universe outside rushes forward in time. Stars shift, galaxies drift, cosmic history accelerates. You become a traveler cut off from the outer world, not by force, but by geometry. The horizon does not harm you, it isolates you. Inside, everything moves inward. Even light cannot remain still. Every path leads toward deeper curvature, even as your body, your senses, your thoughts continue normally until the tidal gradient grows too steep for matter to withstand. So does anything survive crossing the horizon? In the moments after crossing, yes. In any form recognizable to the universe outside, no. And in the language of deep physics, perhaps survival takes a form subtler than we can yet define. As we drift further into this quiet descent, another question emerges with soft inevitability. If nothing violent happens at the horizon, then where does the violence truly begin? Part 6. What did Einstein imagine might lie beyond? Einstein's equations allow for something unexpected, a second region of spacetime connected through the center of a black hole. He suspected the equations might permit a bridge, a hidden path linking distant places or even different universes. He didn't fully trust the idea, but he didn't dismiss it either. To understand how he arrived at such a possibility, we must go back to the early 20th century, when general relativity was still young. Black holes were not yet terrifying astronomical objects swallowing stars. They were simply mathematical curiosities, solutions to Einstein's field equations describing how mass bends spacetime. In 1916, Carl Schwarzschild found the first exact solution, revealing a place where curvature became so extreme that escape became impossible. Einstein initially doubted such regions could exist in reality. Nature, he believed, would prevent such drastic collapse. But mathematics has a way of pushing beyond intuition. The equations did not merely describe a gravitational pit, they hinted at structure beneath the surface. Beneath the event horizon, if one continued the geometry inward, the equations seemed to extend elsewhere, into a mirrored region of spacetime. This extension later became known as the Einstein-Rosen bridge. In 1935, Einstein and physicist Nathan Rosen published a paper proposing that spacetime could fold, connecting two distant points through a tunnel-like structure. They imagined a narrow throat joining separate sheets of spacetime, like two pages of a book touching at a single spot. In theory, traveling through this throat would allow someone to bypass the normal geometry of space, reaching another location faster than light could travel through ordinary space. Einstein was cautious. He did not claim such bridges existed physically. But the equations did not forbid them, and that alone was unsettling and thrilling. The solution assumed a non-rotating, uncharged, perfectly symmetrical black hole. In this idealized model, spacetime does not terminate at the singularity. Instead, it continues into a second region, mathematically distinct from our own. This second region could be another part of our universe, unimaginably far away. Or it could be a separate universe entirely, with its own stars, its own physics, its own timeline unfolding independent of ours. Einstein did not interpret this as evidence for parallel universes. He saw it as a mathematical artifact, a consequence of extending the geometry as far as the equations allowed. But others were willing to wonder whether mathematics was revealing something deeper, something physical. The problem, as Einstein understood immediately, was stability. In the ideal model, the wormhole pinches closed too quickly for anything, not even light, to pass through. The throat collapses before travel becomes possible. The bridge is momentary, like a bubble forming and popping in the surface tension of space-time. Without a form of negative energy or exotic matter, nothing could hold it open. Einstein considered this a sign that nature would not allow such passageways. Yet he never claimed they were impossible, only unsupported. Today, physicists recognize that Einstein's skepticism was justified. Classical wormholes, such as the Einstein-Rosen bridge, collapse instantly. But the fact that they exist mathematically keeps the door open, if not physically, then philosophically. If the universe permits the structure, might something else stabilize it? Some researchers have explored whether rotating black holes, described by the Kerr metric, might behave differently. Rotation introduces a ring-shaped singularity rather than a point, altering the interior geometry. In early analyses, this ring seemed to allow paths through the black hole into another region of spacetime. But modern understanding suggests these paths are unstable, disrupted by even the smallest disturbances. Any real black hole would contain enough cosmic noise, falling gas, radiation, quantum fluctuations, to collapse the bridge. And yet, the idea persists. Einstein found the concept uncomfortable because it invited speculation beyond empirical science. He believed physics should describe nature, not hypothetical shortcuts through it. But he also believed the universe should be explored with humility. If mathematics offers a doorway, it may be unwise to seal it shut without looking in. At the same time, Einstein and Rosen considered these bridges. Physics was grappling with the nature of space itself. The universe had recently been revealed to be expanding. Galaxies were understood as separate islands of stars. Gravity was no longer a force, but a consequence of geometry. In this new framework, space was malleable, flexible, able to stretch, twist, ripple, and curve. Wormholes were simply another geometric possibility. Einstein never believed black holes would form naturally in the universe. He thought stars might resist collapse through radiation pressure or new physics, not yet discovered. The idea of an event horizon swallowing everything was, to him, an extreme extrapolation. But by the late 20th century, observational astronomy proved otherwise. We detected compact X-ray sources orbiting invisible companions. We measured gravitational wave collisions. We imaged the glowing rings of superheated gas spiraling into dark gravitational wells. Black holes were not abstractions. They were real. And suddenly, Einstein's old bridge returned to relevance. If black holes exist, might their internal geometry exist too? Modern physics adds more nuance. Wormholes, if they can be stabilized, may require exotic matter with negative energy density, something never observed in bulk form. Quantum field theory allows tiny fluctuations with negative energy, but scaling them to astrophysical levels remains speculative. Some researchers propose that quantum gravity, the yet unknown theory uniting relativity with quantum mechanics, could modify the interior of black holes, preventing singularities and allowing tunnels to form. Others suggest that every black hole might create a baby universe on the other side, sealed off from our own. In this picture, crossing the horizon would be crossing a boundary not into elsewhere, but into elsewhen. Our universe could be the interior of a black hole formed in a larger parent cosmos. The bridge becomes not a tunnel of travel, but a tunnel of genesis. Einstein would likely have raised an eyebrow at such possibilities, but he would not have dismissed them lightly. He believed that imagination, grounded in mathematics, was essential to progress. Still, Einstein's discomfort with wormholes was rooted in something deeper than skepticism. He believed nature tends toward stability, simplicity, and symmetry. A traversable wormhole seemed too convenient, too easily exploited for paradoxes, violations of causality, shortcuts through reality. If one could step through space in an instant, what would prevent time loops, contradictions, or violations of thermodynamics? For Einstein, the consistency of the universe mattered more than the allure of cosmic bridges. And yet, the equations remain. They continue to whisper that the universe might be bigger, stranger, more connected than observation alone can reveal. When you stand at the edge of a black hole, if such a thing were possible, and imagine what lies beyond, you are not merely guessing. You are following a thread Einstein himself once held, tracing it into the unknown. Whether the other side is a mathematical illusion, a sealed chamber of warped geometry, or an entirely new universe, the idea forces us to question what boundaries actually mean. Perhaps the bridge is not a corridor, but a metaphor, reminding us that the universe contains more than what we currently measure. Or perhaps the bridge is real, waiting for a future physics to unlock it. And as this quiet possibility lingers, one more question rises gently from the darkness. If black holes might connect to elsewhere, then what keeps such bridges from remaining open? Part 7. What exactly is an Einstein-Rosen bridge? In 1935, Einstein and Nathan Rosen discovered a solution to the equations of general relativity that looked like a tunnel between two regions of spacetime. Later called a wormhole, their structure connected two mouths with a narrow throat, bending geometry into a shape unlike anything else known in nature. Whether they can exist in reality is still an open question. To understand what an Einstein-Rosen bridge truly represents, you must think of spacetime not as an empty void, but as a fabric, flexible, stretchable, and able to fold in ways our intuitions rarely imagine. In everyday life, space seems rigid. Distances stay distances, straight lines remain straight. But in Einstein's universe, mass and energy bend the geometry beneath them. Gravity is nothing more than the curvature of that geometry, guiding objects along natural paths. If you take this curvature seriously, if you allow the equations to express their full creativity, you discover that space can fold so dramatically that two distant points touch. Picture a sheet of paper, place two dots far apart. To travel between them normally, you would move across the sheet tracing a long path. But if you fold the paper so the dots touch, you can bypass the long route entirely. The Einstein-Rosen bridge is a mathematical version of this fold, not in 2 dimensions, but in 4. Einstein and Rosen developed their idea from the Schwarzschild solution, the first exact solution to the field equations describing a non-rotating spherical mass. The Schwarzschild geometry leads to a region inside the event horizon where radial coordinates behave strangely. Instead of ending abruptly at the center, the mathematical extension continues into a mirror region. It was this mirror region that suggested the possibility of a tunnel. By sewing these two solutions together, Einstein and Rosen formed a bridge, a throat connecting two sheets of spacetime. One sheet represents our universe. The other could represent another point in our universe, unimaginably far away. Or it could be something more radical, a separate spacetime altogether with its own geometry and cosmic history. The bridge itself has three main components: two mouths, the openings of the wormhole. Each mouth looks externally like the horizon of a black hole. A throat, a narrow tube connecting the two mouths. This is the passageway where space-time folds inward and then outward again. A symmetry. The geometry is perfectly balanced with no preferred direction. This symmetry makes the structure elegant but also unstable. When Einstein and Rosen first proposed this idea, they did not envision wormholes as gateways for travelers. They saw the bridge as a way to remove the troubling singularity at the center of the Schwarzschild solution. By connecting two regions of space-time at the throat, the singularity could be smoothed out mathematically. In this sense, the bridge was part of a thought experiment, an attempt to repair the geometry and make it more palatable. But the universe does not always bend to our desire for elegance. Later research revealed that the bridge collapses too quickly to allow anything to pass through. The throat pinches closed almost instantaneously, sealing the two regions off from one another. The collapse happens so fast that even light cannot make the crossing. This is why Einstein-Rosen bridges are sometimes described as non-traversable wormholes. They exist mathematically, but not physically, at least not without new physics to stabilize them. Still, the imagery remains compelling. Picture yourself standing outside the mouth of such a bridge. From far away, it looks like a black hole, a dark sphere surrounded by curved starlight. But step closer, and the geometry reveals its deeper structure. Instead of plunging into a singularity, space funnels inward and then outward again. The inward flow of space-time reverses at the throat, guiding the path into another region. Einstein understood that any physical realization of this geometry would likely require a form of matter that violates the known energy conditions, matter with negative energy density. Classical physics offers nothing like this, but quantum field theory does. In certain rare configurations, the vacuum itself can take on negative energy relative to a reference state. The Casimir effect is a famous example. Two metal plates placed very close together experience a subtle inward force because the energy between them is lower than the energy outside. Could such quantum effects stabilize a wormhole? Some researchers believe so, others doubt it. What remains clear is that the Einstein-Rosen bridge planted the seed for one of the most enduring ideas in theoretical physics. Modern wormhole research builds on Einstein and Rosen's foundation, but extends it dramatically. For example, traversable wormholes, wormholes you could actually pass through, require exotic matter with specific properties. They must remain open long enough for light or objects to cross. They must have mouths large enough to avoid destructive tidal forces, and they must not collapse into black holes or form singularities. Each of these requirements is demanding. Some verge on impossibility. And yet the mathematics does not forbid them outright. General relativity is flexible enough to allow solutions if the right ingredients exist. Some modern theories suggest that wormholes might be created at the quantum scale, microscopic tunnels flickering in and out of existence in the quantum foam. These tunnels would be unimaginably tiny, far smaller than any particle. They might appear and vanish in less time than an atomic vibration, but in principle, they would represent the same geometry as the Einstein-Rosen bridge, just at a scale where quantum uncertainty dominates. Other physicists propose that if such microscopic wormholes could be inflated, perhaps through exotic energy or cosmic expansion, they might grow large enough to become macroscopic. This idea remains speculative, but it illustrates how Einstein's original concept continues to inspire new directions. The connection between wormholes and quantum mechanics has deepened in recent years. Some theoretical frameworks suggest that entanglement, the subtle quantum link between distant particles, may itself be related to wormholes. In 2013, physicists Juan Maldacena and Leonard Susskind proposed the ER-EPR conjecture, the idea that Einstein-Rosen bridges, ER, and quantum entanglement, EPR, might be two sides of the same phenomenon. If true, every pair of entangled particles could be connected by a tiny wormhole, too small to travel through, but real in a geometric sense. Einstein might have been amused by this idea. He famously disliked quantum entanglement, calling it spooky action at a distance. Yet his own bridges, created to make general relativity more complete, may play a role in explaining the very quantum phenomenon he distrusted. A full understanding of wormholes remains elusive. They may never exist physically. They may require energy conditions that nature does not allow. They may collapse at the slightest disturbance. Or they may flourish in places we have not yet learned to look, hidden in the geometry of black holes, woven into the quantum fabric, or stretching across cosmic inflation in the early universe. But the value of the Einstein-Rosen bridge lies not only in whether it exists, but in what it represents. It shows that spacetime is flexible in ways that defy our intuition. It shows that the universe may contain shortcuts, symmetries, and hidden structures beyond the reach of direct observation. And it demonstrates the power of mathematics to reveal possibilities we might never have imagined. Standing at the mouth of such a bridge, even if only in thought, you are reminded that the universe is larger, stranger, and more interconnected than our senses reveal. Whether the bridge is a tunnel between distant regions or a doorway into deeper physics, it invites a question that feels both ancient and new. If spacetime can fold into a bridge, what happens to the geometry when the bridge collapses? Part 8. Why do most wormholes collapse instantly? The mathematics of wormholes carries a difficult truth. Unless they're stabilized by exotic forms of matter, they collapse faster than anything could enter them. Their throats pinch closed, sealing off the passage before even a photon can cross. In this sense, Einstein's forgotten idea may be less a doorway and more a mathematical shadow. To understand why wormholes collapse, imagine spacetime as a flexible material, stretchable, bendable, able to fold and twist. General relativity treats gravity not as a force, but as a deformation in that material. When mass or energy is present, spacetime curves. When mass moves, spacetime ripples. And when the equations are pushed to their limits, spacetime can twist into a bridge connecting two distant regions. But such a bridge, elegant in mathematics, is fragile in nature. The curvature required to create a wormhole is extreme, far beyond what stars, planets, or ordinary matter can produce. It is a geometry balanced at the edge of possibility, like a soap bubble stretched thin. Any disturbance, even the slightest, pushes the structure toward collapse. A traversable wormhole must remain open long enough for light or matter to travel from one mouth to the other. But the moment you attempt to pass through, your presence disturbs the geometry. Mass warps spacetime, and that extra curvature disrupts the delicate balance holding the throat open. The region collapses inward, cutting off the passage. This collapse occurs so quickly that, in classical general relativity, it is instantaneous. A photon trying to cross the throat would find the passage pinched shut before it could take even a single oscillation. The reason lies in energy conditions, rules that describe how matter and energy are allowed to behave in relativity. Ordinary matter obeys the null energy condition, which states that the flow of energy measured along any light-like path must be non-negative. Wormholes, however, require the opposite. They need matter that produces negative energy density, pushing outward against the pull of gravity. This exotic matter would act like a kind of anti-gravity pressure. Instead of curving spacetime inward, it would curve spacetime outward, propping the throat open. Without this outward pressure, the immense inward pull of curvature slams the tunnel shut. Einstein and Rosen didn't know about exotic matter when they proposed their bridge. They simply saw the geometry and recognized its instability. Later physicists, including John Wheeler, who coined the term wormhole, explored the structure more deeply. Wheeler's investigations revealed the full fragility of these tunnels. Even a single photon passing through, even a tiny quantum fluctuation, would destabilize the throat. In Wheeler's words, wormholes were geons of imagination, beautiful but fleeting. Even if you don't try to travel through, the universe around the wormhole is dynamic. Radiation drifts, particles collide, gravity fluctuates. These tiny disturbances, harmless in ordinary space, become catastrophic inside a wormhole. The throat tries to balance two different regions of spacetime, each tugging on it with different curvatures. Without exotic matter providing outward push, the throat contracts like an overstretched membrane snapping back into place. It helps to picture the wormhole throat as a spherical balloon pressed between two enormous gravitational fields. Unless you constantly pump energy into the balloon, energy that curves space-time in exactly the right way, it collapses. This leads to an uncomfortable truth. Nature does not appear to provide the type of matter needed to keep a wormhole open. All known forms of matter exert positive energy density. They pull inward, not outward. Even the most extreme astrophysical environments, neutron stars, supernova shockwaves, the early universe, do not produce sustained negative energy in the quantity required by a stable wormhole. There are fleeting exceptions. Quantum field theory allows small pockets of negative energy, but only temporarily. The Casimir effect demonstrates this. Between two uncharged metal plates placed extremely close together, certain vacuum modes are suppressed, producing a region with slightly lower energy than the surrounding vacuum. This is negative energy, but it is tiny, unstable, and confined to microscopic scales. If you tried to prop open a wormhole with this effect, the negative energy would fluctuate wildly and cancel out before the throat could expand to macroscopic size. Even worse, quantum inequalities restrict how much negative energy can exist and for how long. These restrictions arise from the uncertainty principle and from the structure of quantum fields themselves. They prevent exotic matter from being scaled up into something that could stabilize a wormhole. In essence, physics allows negative energy, but only in brief and limited flashes, and wormholes require enormous, steady amounts of it. So the classical Einstein-Rosen bridge collapses instantly. The throat pinches shut before any particle can cross. To an outside observer, the collapse looks like a black hole forming and sealing itself. Inside the geometry, the bridge attempts to open and then collapses inward so rapidly that even light cannot traverse it. This collapse is not violent, it is smooth and complete. Space simply folds inward, erasing the connection. But there is a subtle twist. In the fully extended geometry of the Schwarzschild solution, the wormhole exists for a single moment, an instant of cosmic housekeeping where space-time connects two regions before sealing them off. This moment is purely theoretical, existing only on paper. In an actual astrophysical black hole formed from a collapsing star, the interior geometry is different. The wormhole structure never appears. The singularity forms before any bridge can fully emerge. In this sense, the Einstein-Rosen bridge is a relic of idealized mathematics, a shape space-time could take under perfect symmetry, but one it does not naturally produce in reality. Still, the idea persists because the collapse hints at deeper truths. If nature resists wormholes so strongly, what does that say about space-time itself? Perhaps the universe guards its causal structure, preventing shortcuts that could lead to paradoxes. Wormholes could allow time travel or violations of causality if left unchecked. Their collapse may be the universe's way of preserving order. Yet the story becomes more interesting when quantum mechanics enters the picture. Quantum entanglement links distant particles in ways classical physics cannot explain. And some modern conjectures, most famously ER-EPR, suggest that wormholes and entanglement might be two expressions of the same phenomenon. In this view, wormholes are not stable tunnels you can traverse, but deep geometric relationships between distant points in space-time. If such a relationship collapses instantly, perhaps the collapse is not a failure, but a signal. It may be telling us that wormholes are not meant for travel, but for understanding. They illustrate how space-time behaves at its limits, how quantum information might be stored or connected, and how geometry can express relationships that no classical picture can capture. Even if wormholes cannot remain open, they reveal something profound about the universe. Space-time contains possibilities that stretch far beyond our intuition, but nature chooses which of those possibilities become real. Their collapse is not a disappointment, but a reminder that mathematics is larger than reality, that the universe selects only the geometries that preserve its deep consistency. And as this quiet truth settles, another question rises with gentle inevitability. If wormholes collapse so quickly, then what, if anything, could keep one open? Part 9. Could a black hole and a white hole be opposites? A white hole is the theoretical reverse of a black hole, a region where nothing can enter, only escape. Some physicists once wondered whether the interior of a black hole might connect to a white hole on the other side. The idea never became mainstream, but it continues to inspire new models, new equations, and new dreams of cosmic symmetry. To understand why this idea emerged in the first place, we need to revisit what makes black holes so unique. A black hole is defined by one essential feature, its event horizon, a boundary through which nothing can escape. The moment an object crosses the horizon, its future becomes sealed. Every possible path through spacetime leads deeper inward, and none lead out again. This one-way structure is not a force, but a consequence of geometry. Inside the horizon, moving outward becomes as impossible as moving backward in time. Now, imagine a mirror version of that geometry. Instead of a region where nothing can escape, imagine a region where nothing can enter. Any particle approaching the horizon would be flung away before crossing. Inside, spacetime would funnel outward instead of inward. This is the idea of a white hole, a mathematical solution consistent with Einstein's equations, far stranger than a black hole and far less forgiving. In the 1960s, when general relativity was undergoing a renaissance, physicists studied these solutions with growing fascination. If black holes represented one extreme of space-time curvature, white holes represented the other. If black holes swallowed matter, white holes expelled it. If black holes erased the past of anything that fell inside, white holes erased the future of anything that attempted to approach. A white hole, in its pure form, behaves like a cosmic fountain, a place where light, matter, and information pour outward endlessly, and nothing can ever penetrate its horizon. The symmetry is beautiful, elegant, but nature may not be obliged to follow beauty. White holes, like wormholes, first appeared as mathematical extensions of the Schwarzschild solution. If you extend the geometry beyond the black hole interior, beyond the singularity predicted by classical relativity, you find a second region where trajectories point outward. In the most literal interpretation, this second region is a white hole. The question then was not whether the equations allowed them. They did. The question was whether the universe did. Early enthusiasm faded as physicists studied the stability of these structures. White holes turn out to be profoundly unstable. Any small perturbation, a stray particle, a photon, even the whisper of radiation, would destabilize the outward flow. Because nothing can enter a white hole, even the attempt breaks the solution. The horizon crumples, the geometry collapses, and the white hole disappears. A black hole can persist for billions of years. A white hole cannot last a moment. Its very existence would demand a perfectly sealed environment. No matter, no dust, no radiation, no fluctuations, which does not exist in our messy universe. Yet the idea did not die. Instead, it evolved. Some researchers wondered whether a black hole's interior might transition into a white hole without requiring the universe to build one from scratch. If matter collapsing into a black hole eventually triggered a quantum bounce, like a compressed spring recoiling, perhaps the interior could reverse its orientation. Instead of funneling inward forever, spacetime might re-expand, forming a white hole phase on the other side. In this picture, the singularity is not a point of infinite density, but a transitional region where quantum gravity becomes dominant. Matter falling into the black hole does not remain trapped eternally. It re-emerges through a white hole, perhaps even into a different region of spacetime long after the black hole forms. The timescales involved are enormous. From the interior perspective, the bounce might occur quickly, but from the outside, immense time dilation stretches the process into trillions of years. A black hole could appear stable, enduring, unchanged for most of cosmic history, only to expel its contents in a white hole eruption long after the universe has grown cold. This idea, while speculative, has been explored in several loop quantum gravity models. It offers a tantalizing possibility that black holes do not erase information but store it, transform it, and release it later in an entirely different form. Others propose that a black hole-white hole pair may form the two mouths of a wormhole. In this scenario, a traveler entering a black hole would emerge from a white hole elsewhere, bypassing ordinary space. But this idea suffers from the same instability problems that plague classical wormholes. Any attempt to travel through the throat destabilizes the structure. The geometry collapses before the journey can complete. Still, the symmetry remains irresistible. Black hole, nothing escapes. White hole, nothing enters. Together, a complete mirrored structure of spacetime flow. Some physicists consider this symmetry a clue, not a literal connection, but a hint about the structure of gravitational collapse. Perhaps the universe does not create white holes, but the mathematics suggests how spacetime behaves near singularities. It may point toward a deeper truth hidden in the interplay between relativity and quantum mechanics. There is another reason white holes remain fascinating. They resemble the Big Bang. The Big Bang, in its simplest description, is a white hole in reverse. It is a place where matter and energy erupt outward from a boundary that cannot be traced to a previous region of spacetime. Nothing could have entered the Big Bang. Everything emerged from it. In this sense, the universe itself began in a white hole-like state. This resemblance has sparked speculation that every black hole might birth a new universe. In this view, crossing the horizon of a black hole in our universe could be equivalent to crossing the horizon of a Big Bang in another. The black hole interior funnels inward until quantum effects create a bounce. On the other side, space-time expands, creating a new cosmos with its own laws and constants. We may be children of such a process, born inside a cosmos formed through a black hole's rebound in an older universe. Einstein, who had an intuitive sense for symmetry, might have appreciated the elegance of this idea, even if he remained cautious. He believed nature often expressed itself through balance and harmony, but understood that symmetry could conceal complexity. A white hole, despite its graceful definition, might be too perfect to exist physically. Yet the mathematics remains. And mathematics has a way of revealing possibilities the universe may choose to express in forms we don't yet understand. Even if the classic white hole never forms in nature, its conceptual existence serves a purpose. It reminds us that spacetime can be more flexible, more layered, and more imaginative than we assume. It forces us to confront the nature of boundaries, where they lead, what they hide, and how deeply they connect to the structure of reality. As you drift deeper into the idea of black holes and white holes as opposites, a final question rises quietly. If white holes cannot form freely, could something else mimic their behavior? An echo, a reflection, or a hidden region that behaves like one without truly being its opposite? Part 10. What do modern theories predict inside the horizon? Most classical models say the center of Fueno, a black hole, holds a singularity, a point of infinite density. But modern physics suspects nature avoids infinities. Quantum gravity theories suggest the singularity might instead be a region of extreme but finite curvature, where space and time fold into unfamiliar patterns we don't yet fully understand. To step inside the horizon, at least in thought, is to move into a region where our familiar laws begin to lose their meaning. Outside the horizon, space and time behave with reassuring consistency. Distances have direction, time moves forward with steady rhythm, light follows predictable paths, but once you cross the boundary, these certainties dissolve. The horizon marks the point where geometry becomes destiny. Every possible future leads inward, and the interior becomes a place where the universe's deepest questions gather. The classical picture of a singularity comes from Einstein's general relativity, which describes how mass curves spacetime. In this model, if mass collapses beyond a certain point, the curvature becomes so extreme that all paths converge to a single point of infinite density, a place where the equations break down. But infinities in physics are often signs that a theory is incomplete. They don't describe reality, they describe the limits of our understanding. General relativity, as elegant as it is, cannot describe what happens when densities approach the Planck scale, the realm where quantum mechanics must take over. At those scales, spacetime itself becomes grainy, uncertain, and subject to fluctuations. Quantum mechanics insists that nothing can be infinitely small or infinitely dense. Instead, it predicts that space and time themselves must transform into new forms, governed by principles we have not yet fully uncovered. This is where modern theories step in. They suggest that the singularity predicted by classical relativity is replaced by something else, something finite, structured, and deeply strange. One leading idea comes from loop quantum gravity, a theory that attempts to quantize spacetime. In this model, space is composed of discrete loops, tiny indivisible units woven together into a network called a spin foam. As matter collapses inward, the density grows, but at a certain point, these loops resist further compression. The inward motion halts and rebounds, much like a spring compressed to its limit. Instead of a singularity, the black hole interior becomes a region where space-time bounces, creating a quantum bridge to another region. Some loop quantum gravity models suggest that the core of the black hole might briefly enter a white hole phase, expelling matter into a new region of spacetime long after the black hole forms. In this picture, black holes do not destroy information, they transform it and release it elsewhere, though perhaps across incomprehensible spans of time. Another approach comes from string theory, which replaces point-like particles with vibrating strings of energy. In string theory, the singularity might be replaced by a stringy core, a region where the usual concept of distance breaks down. The collapsing matter does not reach infinite density because strings cannot be compressed beyond a certain limit. Instead, the interior could become a swirling mass of tangled, vibrating filaments, forming a new state of matter that exists only under extreme curvature. Some versions of string theory propose that the interior of a black hole is dominated by a structure known as a fuzzball. In this model, the black hole is not empty inside. Instead, it is filled with quantum threads, microstates that store information and prevent the formation of a classical singularity. A fuzzball has no sharp boundary or central point. Its interior is a tangled, chaotic region of quantum structure, preventing the collapse to infinite density. These modern theories share one central idea. The singularity is not a point of destruction, but a frontier of transformation. To visualize what might happen inside the horizon, imagine space behaving not like a smooth surface, but like a turbulent fluid. Distances warp, directions fold. Time may stretch, twist, or fracture into patterns our minds cannot easily represent. The light cones, the shapes that define how objects move, tilt so sharply inward that all motion becomes a flow toward deeper curvature. But at the core, instead of a point, you encounter something more intricate, a geometric storm where quantum rules replace classical ones. This region is so extreme that our familiar language falters. Space might not be a place in any usual sense. Time might not be a continuous flow. Instead, spacetime could behave like a network of quantum interactions, each flashing into existence for an instant before giving way to the next. In some models, the interior resembles a chaotic quantum foam. In others, it resembles a bouncing, expanding bubble of spacetime. One of the most surprising predictions comes from certain interpretations of quantum gravity. The black hole interior might connect to a new expanding region, potentially even a new universe. In this scenario, every black hole becomes a seed. Matter collapses, compresses, undergoes a quantum transformation, and then expands into a newborn cosmos on the other side. From our perspective, this expansion is invisible. The horizon seals the interior off from us. But from the interior perspective, the bounce might feel like the beginning of a Big Bang. This idea is not proven, but it is not forbidden either. Modern theories also address the fate of information. Classical relativity predicts total destruction. Quantum mechanics insists information must survive in some form. The clash between these two ideas is the black hole information paradox, one of the most profound puzzles in physics. If the singularity is replaced by a quantum region, then information may be stored there, encoded in the microscopic structure of spacetime. It might re-emerge through Hawking radiation, or it might escape through a quantum bounce. The key point is that modern models avoid the permanent erasure that classical singularities demand. Another important aspect of modern theories is their treatment of causality. The classical singularity marks the breakdown of predictable physics. But if the singularity is removed, then spacetime may remain well-behaved, even in regions of extreme curvature. Quantum gravity may restore causality by ensuring that the interior geometry never collapses to a point, but instead reorganizes itself into new structures. Inside the horizon, spacetime becomes dynamic. It evolves, it reacts, it reshapes itself according to laws we have only glimpsed. What appears from the outside as a simple funnel into nothingness is, on the inside, a complex landscape, a region where matter, energy, and geometry dance according to deeper principles. In some models, the interior is not even a place. It is a process, a transition from one state of spacetime to another. The core becomes a phase change, like water turning to ice, but in dimensions far beyond our intuition. What you experience is not a point, but a transformation in the nature of reality. And yet, this picture remains incomplete. We lack the full theory to describe these regions. We have only hints, glimpses from mathematics, clues from quantum theory, and whispers from the edges of black hole physics. What modern theories agree on is this: the classical singularity is almost certainly not real. Nature avoids infinities. And the interior of a black hole is richer, stranger, and more dynamic than Einstein could have imagined. As you drift deeper into this unseen realm, another question stirs quietly in the dark. If quantum gravity reshapes the singularity, what does that mean for the matter and the information that falls inside? Part 11. Could information ever re-emerge? Black holes appear to erase information permanently, which clashes with the rules of quantum mechanics. This paradox has pushed some of the greatest minds in physics to reconsider what a black hole truly is. Some theories suggest the information might be encoded in the horizon itself, stored in subtle ripples of spacetime. To see why this question is so profound, you must picture what information means in physics. It is not just data or memories or the arrangement of atoms in a book. Information describes the structure of a system, the quantum state of every particle, every field, every interaction that has ever shaped it. Information is the universe's bookkeeping, the underlying record of how matter and energy have evolved. Quantum mechanics insists that this information is never destroyed. It can change form, scatter, transform, or become unrecognizable, but it cannot be erased. This is not a philosophical preference. It is a core principle woven into the mathematics of quantum evolution. Black holes seem to violate this rule. When matter falls into a black hole, its details, its quantum state, appear to vanish. Classical general relativity predicts that everything collapsing inside is compressed into a singularity of infinite density, erasing all distinctions. Two identical black holes could be formed from entirely different materials: a collapsing star, a cloud of gas, a planet, or a quantum computer, and from the outside, they would look identical. Their horizons would have the same mass, same charge, and same spin. No trace of their interiors would be visible. This is the essence of the no-hair theorem. Black holes have no hair, no details, no identifiers beyond a few simple parameters, but quantum mechanics protests. It tells us that if information is truly lost, then the fundamental laws of physics break. And so began one of the most important debates in modern physics, the black hole information paradox. Stephen Hawking famously argued that information is lost. Many quantum theorists argued the opposite, and for decades the paradox seemed unresolvable. Then came a shift, subtle at first and then revolutionary. Hawking radiation, the faint glow emitted by black holes due to quantum effects near the horizon, implies that black holes slowly evaporate over time. If Hawking radiation is purely random, then the information that fell in is truly lost. But if the radiation encodes information, If it carries subtle correlations, then the information might re-emerge slowly as the black hole evaporates. The puzzle, then, is whether Hawking radiation is random or structured. To understand how information might survive, imagine the event horizon not as a smooth boundary, but as a dynamic surface filled with quantum fluctuations. According to some theories, these fluctuations store information in microscopic degrees of freedom. The horizon becomes a kind of holographic screen, a surface encoding what lies inside, much like a two-dimensional hologram can represent a three-dimensional object. This idea is the foundation of the holographic principle, a radical concept suggesting that information about a region of space can be stored on its boundary. In the context of black holes, it means the interior is encoded in tiny distortions of the horizon. The black hole becomes not a featureless void, but a densely packed ledger of quantum information. From this perspective, the information is not lost. It is scrambled, spread across the horizon in patterns finer than anything we can detect, but theoretically retrievable. In some models, as the black hole evaporates, these subtle patterns influence the properties of Hawking radiation. The radiation becomes entangled with the interior information. Over immense timescales, the information leaks back out, encoded in faint correlations between the emitted particles. To a casual observer, the radiation appears random, but to an ideal observer capable of detecting these correlations, the information would be reconstructible. This is not just speculation. Recent work using the mathematical machinery of quantum gravity and the holographic principle has shown that such a process is possible. Black holes might act like quantum scramblers, mixing information rapidly but not erasing it. Another idea, coming from string theory, suggests that black holes are not empty with a singularity at the center. Instead, they are fuzzballs, dense bundles of strings and brains. In this model, the interior is filled with microstates that store information directly. The horizon is not smooth but textured by these states. Hawking radiation emerges from these microstates, naturally carrying information with it. The fuzzball picture avoids the paradox entirely. Because there is no empty interior and no singularity, information never disappears into a void. It remains encoded in the structure of the fuzzball and leaks out gradually. Other physicists propose a different interpretation. Perhaps the horizon itself is replaced by a quantum membrane, a firewall, where information is violently released before anything can cross. This idea solves the information paradox, but breaks the equivalence principle, a cornerstone of relativity. If the horizon is a place of violent physics, the smooth passage predicted by general relativity fails. Most physicists resist this idea because it destroys the calm interior journey predicted by relativity. The universe rarely discards a beautiful symmetry unless forced. Another viewpoint suggests that black holes behave like mirrors. Information falls in, becomes scrambled, and then reflects outward through subtle quantum processes. This is analogous to how chaos theory behaves, where small initial differences grow into large final differences, yet the system remains deterministic. And then there is one more possibility. Information might never need to re-emerge because it was never truly lost. According to the ER-EPR conjecture, entangled particles are connected by tiny wormholes, Einstein-Rosen bridges. If this idea extends to black holes, then the interior might be geometrically connected to the outside via quantum entanglement. In this scenario, information falling in becomes entangled with outgoing Hawking radiation. The wormholes connecting these entangled states could allow information to flow out in subtle, non-classical ways. This is not traversable in the usual sense. It does not allow travel or signals, but it ties the interior and exterior together in a single quantum geometry. The horizon becomes a doorway, not in space, but in information. Despite these ideas, no definitive answer exists. We have strong clues, compelling frameworks, and deep insights from quantum gravity, but not the final theory. What we do know is this: the paradox has shifted. Most physicists now believe information is not destroyed. The old view of the black hole interior as a silent eraser has been replaced by a new, richer picture of a region filled with structure, encoded information, and quantum complexity. And so the question, could information ever re-emerge, becomes both simpler and deeper. Yes, most likely it does, but how it re-emerges and what form it takes remains an open mystery. Perhaps it comes out as subtle correlations in Hawking radiation. Perhaps it is stored on the horizon itself. Perhaps the interior and exterior are unified through quantum geometry beyond our current understanding. The truth is still forming, still unfolding, like a faint signal rising from the horizon. And as we move deeper into this story, another question emerges with quiet inevitability. If information can escape in subtle quantum ways, then what becomes of the space and time that cradle that information inside the black hole? Part 12. What happens to space and time at the core? As you move inward, space-time becomes less like a landscape and more like a flowing current. Paths that once made sense no longer behave the same way. Distances collapse, directions blur. The geometry becomes so curved that even the notion of downward loses meaning. To understand what truly happens as you drift toward the core of a black hole, you have to let go of the intuition shaped by normal space. Out here, location is something you can point to. Direction is something you can gesture toward. Distance is something you can measure with a straight line. But inside a black hole, these simple ideas lose their stability. The rules that shaped every moment of your life begin to stretch, fold, and twist until they resemble something entirely new. Inside the horizon, space doesn't behave like the space you know. The inward direction becomes as inevitable as the passage of time. No amount of thrust, no force, no motion can push you outward again. Space-time funnels all possible paths toward the center, not because you are being pulled, but because the geometry itself is curving in a way that leaves no alternatives. The closer you move toward the core, the more extreme this funnel becomes. It is not a tunnel or a channel, it is more like the narrowing of time itself. The inward direction becomes the future. The center becomes the destination not because it pulls you, but because every possible future leads there. In Newtonian physics, gravity acts like a force, pulling masses together. But inside a black hole, Einstein's view takes over completely. Gravity is geometry. You aren't being dragged, you're gliding along the natural contours of space-time. These contours, near the core, are steep and unstable, curving inward faster than anything can resist. This curvature grows stronger with every inward step. The tidal forces, differences in gravitational pull between different parts of your body or your spacecraft, begin to intensify. In the outer layers of a supermassive black hole, these forces are gentle, but deep inside, they begin to stretch objects along one axis and compress them along another, not violently at first, but steadily, like the tightening of an invisible grip. Near the core, this stretching accelerates. Distances that once mattered begin to collapse. Everything that falls inward is compacted along the same direction, funneled toward the same fate. The geometry becomes so extreme that the notion of maintaining shape becomes impossible. Matter begins to behave in ways no earthly material could withstand. But even these descriptions rely on the classical picture, a singularity at the center where density becomes infinite. And as we have explored, modern theories suspect that such infinities do not exist in nature. Instead, something else waits at the core, something more structured, more complex, and far stranger than the equations of classical relativity can describe. If loop quantum gravity is correct, then space-time itself becomes discrete at incredibly small scales. It is woven into tiny loops that resist collapse. As matter falls inward, space-time cannot shrink to a point. Instead, it reaches a minimum size and rebounds. The core becomes a region of maximum compression followed by expansion, a quantum bounce where space does not end but transforms. In this vision, the core is not a point, it is a transition, a place where the inward flow of space-time halts and reverses. The geometry becomes a knot of quantum loops oscillating with energy, preventing the collapse to infinite density. If string theory is correct, the core might be filled with vibrating filaments, strings stretched to their limit. The matter that falls inward does not reach infinite density, but instead dissolves into extended objects that cannot be compressed beyond a certain threshold. The geometry of spacetime responds by forming a dense, chaotic region where distances shrink but never vanish. If fuzzball theory is correct, the interior is not empty at all. The entire region is filled with quantum microstates, rich, tangled layers of geometry. The core is not a place where everything collapses. It is a place where everything already is. You are not falling into a void. You are falling into a structure. Every particle, every piece of information is stored in this quantum foam, preventing the singularity entirely. All of these theories agree on one point. The core is not empty, and it is not a point. It is something else, something dense, dynamic, and deeply quantum. But even if the singularity is smoothed out, the geometry near the core remains extreme. The normal separation between space and time dissolves. Light cones tip so severely inward that motion becomes almost indistinguishable from falling deeper into time itself. Spatial directions, up, down, sideways, lose their independence. The inward direction is no longer just a direction. It is the unfolding of your future. One of the strangest consequences of this geometry is that time itself becomes distorted in ways that defy intuition. The closer you get to the core, the faster your internal clock seems to run relative to the curvature outside. The tidal forces compress not only matter, but time. The boundary between past and future blurs. Space-time becomes a continuum where the usual distinctions between moments dissolve. The classical singularity is the limit of this collapse, a place where space-time curvature becomes infinite. But quantum effects step in before that limit is reached. The interior becomes turbulent, chaotic, and deeply structured. The geometry fluctuates. The fabric of space roils like a storm, not in 3 dimensions, but in all dimensions at once. Particles entering this region behave unpredictably. Their paths are twisted, bent, spun, and folded. The geometry affects their quantum states, scrambling information but not destroying it. Some theories suggest that trajectories are not smooth curves, but fractal-like paths shaped by quantum fluctuations. Others propose that particles lose their identity entirely, merging with the quantum structure that fills the core. From inside this region, the idea of a center becomes meaningless. There's no point to reach, no destination. Instead, the core is a region, a domain where space-time enters a new phase. It is similar to how water becomes ice or plasma becomes gas, but on a scale and in a form totally incompatible with daily experience. The interior might resemble a quantum whirlpool, where geometry, information, and matter intertwine. It might resemble a region of pure potential, where space-time is so compressed that expansion becomes inevitable. It might resemble a bridge to another region of space-time, a rebound or extension beyond the classical geometry. What is certain is that nothing maintains its identity unaltered. Space changes, time changes, the rules change. Yet through this transformation, a quiet truth persists. The laws of physics do not vanish at the core. They evolve. They reveal deeper levels of reality hidden beneath the classical world we normally inhabit. The core of a black hole is not the end of physics. It is the beginning of a new regime. And as we drift deeper into this possibility, a new question arises with gentle inevitability. If space and time lose meaning at the core, then what does it mean for a black hole to connect to somewhere or something beyond itself? Part 13. Could black holes be gateways to new universes? Some cosmologists propose that each black hole might seed a new expanding region of spacetime, its own universe branching off from our own. In this view, our universe might itself have emerged from the interior of another black hole, nested like a quiet echo inside an older cosmos. To explore this idea, you have to let go of the image of a black hole as a dead end. In the classical picture, a black hole is a collapse, matter falling inward, curvature rising without limit, the interior shrinking toward a singularity where all further evolution stops. But modern theories, as you've seen, increasingly suspect that nature resists singularities. Instead of ending, the geometry might transition. Instead of collapsing forever, spacetime might rebound. And if that rebound expands, if it unfolds into a new region of spacetime, then the inside of a black hole might not be an ending at all, but a beginning. Picture, for a moment, the early universe. The Big Bang was not an explosion in space, it was an explosion of space. A tiny region of extreme density underwent rapid expansion, creating new dimensions, new fields, new laws. It grew from a quantum-sized seed to a cosmic-scale space in fractions of a second. This expansion erased whatever came before, smoothing out irregularities, stretching fluctuations into the seeds of galaxies. Now, picture the interior of a black hole at the moment quantum gravity prevents collapse into a singularity. The densities are immense. The curvature is extreme. Quantum effects dominate. This region, too, could undergo expansion, an inflationary burst triggered by the same vacuum energy mechanisms that drove our own early universe. To someone living inside that expansion, the outside universe would be inaccessible. The horizon of the black hole becomes, from the inside, a boundary like the edge of a cosmic beginning. What we call a black hole, observers inside would experience as a Big Bang. This idea is known as cosmological natural selection, or sometimes black hole cosmogenesis. It suggests that universes can reproduce, spawning new universes through the interiors of black holes, each with slightly different physical constants. Our universe may be one such offspring, its laws shaped by the conditions of a parent cosmos. In this vision, black holes become the cosmic equivalent of seeds, each one carrying the potential to bloom into a universe of its own. The idea is speculative, yet rooted in real mathematics. The transition from collapse to expansion appears in several quantum gravity models. Loop quantum cosmology predicts that when densities reach the Planck scale, a bounce replaces the singularity. The interior geometry changes direction, shifting from inward collapse to outward growth. In the language of the equations, the time coordinate flips orientation. Collapse becomes birth. Other frameworks, such as certain versions of string theory, allow similar transitions. The compact dimensions of string theory can store energy that becomes dynamically active under extreme conditions. The collapse stretches these dimensions to the limit, the bounce releases them. The new universe that forms inherits this geometry. But if every black hole births a universe, how are these universes connected? Do they share spacetime? Are they embedded inside one another? Or are they entirely separate realms linked only through the geometry of quantum transitions? Most versions of the idea suggest that daughter universes are disconnected from their parents. They do not occupy the same space. Instead, they emerge on the other side of a bounce in a region insulated by quantum geometry. The black hole horizon becomes a one-way membrane. Information entering the black hole becomes part of the seed conditions for the next universe. But no signal can travel back. To us, the black hole looks like an object. To the new universe inside, the black hole looks like a beginning. This perspective raises a profound possibility. Our universe may not be the first. It may not even be the only one. It could be one link in an enormous cosmic lineage, stretching backward and forward through countless generations of universes. Some cosmologists go even further. They propose that the physical constants we observe, gravity's strength, the mass of the electron, the charge of the proton, the cosmological constant, might be fine-tuned for black hole production. Universes that produce many black holes generate many daughter universes. Those that produce few black holes generate fewer. Over time, universes with laws that efficiently create black holes become more common. In this sense, black holes drive an evolutionary process, not of biological organisms, but of entire universes. The cosmos becomes a family tree, each universe passing down its physical traits in a quiet, generational chain. This is not mainstream physics. It is not proven. But it is not fantasy either. It flows naturally from modern theories that replace singularities with transitions, and it provides an intriguing resolution to questions that have puzzled cosmologists for decades. Why do the laws of physics allow stars to form? Why are black holes stable? Why is the universe capable of generating such intricate structures? It might be that we are living in a universe shaped by generations of cosmic evolution. But this picture carries a subtle implication. If our universe emerged from the interior of a black hole in another cosmos, then our own black holes may contain new universes forming right now. These universes would be invisible to us, sealed behind horizons we cannot cross. We would never detect them directly, but we might infer their presence through the mathematics of quantum gravity or the patterns of physical constants in our own universe. In some models, every collapsing star in our universe gives rise to a new universe beyond its horizon. Other models suggest that only certain types of black holes produce universes, supermassive black holes, or those formed under specific quantum conditions. And still others propose that only the very first black holes, formed in the earliest epochs of the cosmos, generate new regions. In all versions, however, the idea shares a common thread. The end of one region of spacetime becomes the beginning of another. This idea transforms our understanding of what a black hole is. It is no longer a cosmic prison. It is no longer an eraser. It becomes a boundary, a membrane between realms, a quiet doorway that opens only in one direction. But even as we imagine these new universes blooming beyond our reach, questions gather softly around the edges. What laws do these daughter universes follow? How do their constants differ? Could they host stars, galaxies, life? Or are they barren regions of geometry and vacuum energy? Do they inflate eternally? Do they collapse quickly? Do they have time? We cannot know. The horizon seals them away. The geometry prevents any signal from traveling between parent and child. The lineage is silent, its generational memory carried not by messages, but by structure. And yet, this idea leads toward a deeper question, one that whispers through the mathematics of black holes and the structure of spacetime. If a black hole can spawn a universe, if every collapse becomes a beginning, if spacetime can curl in on itself and then unfold into something new, then what lies at the boundary between one universe and the next? As you drift toward this question, the next part awaits with quiet inevitability. How does gravity itself shape the flow of information, geometry, and time as universes branch, evolve, or emerge from one another? Part 14. What if the other side is simply more spacetime? Not every theory is dramatic. Some physicists argue that the interior may be nothing more than a continuation of spacetime, stretched into forms we haven't yet mapped. No tunnels, no bridges, just gravity rearranging geometry in a way that feels alien to intuition but obedient to the laws of physics. This view, though humble compared to wormholes and new universes, is in many ways the most grounded. It does not require exotic matter, quantum bounces, or hidden expansions. It simply extends Einstein's vision inward, following the contours of curved spacetime to their natural conclusion. In this picture, a black hole is not a doorway to somewhere else. It is simply a region where the fabric of reality is shaped into unfamiliar patterns. To understand this perspective, imagine spacetime not as a static grid, but as a dynamic, flexible field. Far from massive objects, the field is flat, smooth, and predictable. Closer to stars and planets, it dips gently. Around dense remnants, neutron stars, white dwarfs, the curvature becomes deeper and sharper. A black hole is the extreme of this continuum, a region where the curvature becomes so steep that every possible future points inward. But this curvature does not necessarily imply a rupture. It may simply continue, becoming increasingly complex without forming bridges or bounces. In this view, there is no other side. There is only interior geometry, intense, distorted, but still part of the same spacetime manifold. Inside the horizon, the radial direction becomes temporal. Movement toward the center is as unavoidable as moving forward in time. But this does not mean that space ends. It means that the structure of spacetime evolves. Directions lose the meaning they once had. Distances behave differently. Time itself becomes intertwined with curvature. Some models of classical general relativity suggest that inside the black hole, space-time stretches in ways we have yet to visualize. The metric, the mathematical object describing distances, changes character. Instead of indicating a singular point, the equations may describe a region where space becomes elongated, like a funnel that narrows but never fully closes. In this picture, the singularity may not be a point at all. It may be a region of extended geometry, distorted into a shape the equations only approximate. The infinite density, predicted by naive interpretation, may be an artifact of assuming space-time remains smooth at all scales. If space-time becomes granular or turbulent at quantum levels, the singularity dissolves into a structured zone of extreme curvature. Seen this way, the black hole interior is not a rupture in the cosmos. It is a new landscape, one hidden behind a horizon we cannot cross back through, but not one that breaks the unity of space-time. This idea finds support in the mathematics of relativity. The maximally extended Schwarzschild solution describes a space-time where the interior is not a cutoff, but a continuation. The coordinates change behavior, time and space trade roles. The interior is a region with its own causal structure, but it remains part of a single manifold. Some theorists imagine the interior as a kind of stretched space-time tunnel, not a traversable wormhole, but an elongation. The inward direction becomes increasingly compressed in some dimensions and expanded in others. The structure resembles a throat, yet this throat leads not outward to another universe, but inward to a region where geometry simply ends at a boundary imposed by classical equations. Quantum theories soften this boundary, but they do not necessarily replace it with something as dramatic as a new universe. Instead, they may create a core with finite curvature, finite density, and complex geometry, the endpoint of collapse, but not the beginning of anything else. In this view, the interior is mysterious but not fantastical. Some physicists liken it to a geological cavern that no one has mapped, vast, dark, filled with unseen structures, yet ultimately part of the same world. Others compare it to the deep ocean trenches on Earth, regions where pressure, temperature, and darkness create unfamiliar conditions, but where physics still governs without requiring new realms. This modest interpretation may feel less extravagant than theories of baby universes, but it offers an elegance of its own. It preserves the unity of space-time, it honors general relativity's geometry, and it avoids multiplying entities without necessity. A key insight of this view is that the horizon is not a boundary between universes. It is a boundary between regions of the same universe. Crossing it does not move you somewhere else, it moves you deeper into the curvature. As you drift inward, the geometry changes in subtle and then dramatic ways. Distances between objects shrink faster than you would expect. Light cones tilt inward more sharply. Space stretches differently along different axes. The curvature becomes anisotropic, meaning different directions curve differently. This anisotropic structure makes the interior feel alien, but not disconnected. One possible structure, predicted by certain classical extensions of relativity, is the BKL singularity, a chaotic region where space-time oscillates wildly. Instead of collapsing smoothly, the core geometry undergoes repeated contractions and expansions in different directions. These oscillations become increasingly rapid as you move inward. The geometry becomes turbulent, like a storm in space-time, but still within the confines of a single universe. Quantum gravity may smooth these oscillations, softening the turbulence but keeping the continuity. The interior becomes a region of dense space-time foam, intricate, fluctuating, and mathematical rather than material. In this view, nothing in the black hole interior requires a new universe. The strangeness arises not from new realms, but from extreme curvature, applied to the same laws we already know. The interior becomes a natural extension of the cosmos, not a portal. This interpretation also aligns with the holographic principle. If information is stored on the horizon, then the interior may act as a kind of geometric placeholder, a region whose structure ensures the consistency of the information encoded on the boundary. The interior need not produce new universes. It only needs to preserve the consistency of the one we already inhabit. This picture also respects cosmic censorship, the idea that singularities, if they exist, are always hidden behind horizons. The interior remains inaccessible and invisible, ensuring that its extreme geometry never disrupts the orderly physics of the outside universe. It is a quiet theory, almost humble in its restraint. But there is a kind of beauty in this restraint. It does not ask for new dimensions or unseen universes. It simply extends the elegance of general relativity inward, letting the curvature speak for itself. In this light, the interior of a black hole becomes a reminder that the universe does not need to be spectacular to be profound. It can be strange without being exotic, alien without being fantastical, deep without requiring a doorway to somewhere else. Yet, even within this restrained view, questions linger softly. If the interior is simply more spacetime, distorted, stretched, unfamiliar, what determines the final shape of that geometry? How does it evolve over time? What roles do quantum effects play as matter approaches its most compressed state? Are there hidden patterns in the curvature? Does the interior remain static, or does it pulse with quantum fluctuations? This quieter vision, though modest, invites a final question with gentle inevitability. If the other side is simply more spacetime, then what does that spacetime ultimately lead to? And does anything emerge from its deepest folds? Part 15. Why does this mystery matter so deeply? Black holes sit at the crossroads of gravity, quantum mechanics, and the nature of reality itself. They are not merely exotic objects. They are laboratories where the universe pushes its own rules to the breaking point. Whatever lies beyond them, whether nothing or something more, reveals how our cosmos truly works. To understand why this mystery matters, imagine the universe as a vast book. Most of its chapters are legible, its pages are structured, its paragraphs orderly. Stars move along predictable paths, galaxies rotate with quiet precision, space expands with a rhythm we can measure. But black holes are the hidden chapters, the pages where the text bends, the ink smears, and the narrative becomes so strange that ordinary language fails. They are the places where our understanding reaches its limits. The rules that guide everyday physics, rules that work flawlessly for planets, atoms, and light, begin to contradict one another near a black hole. Gravity insists on one thing. Quantum mechanics insists on another. And in the midst of these contradictions, the universe reveals that something deeper must exist beneath both frameworks. This is why black holes matter. They expose the frontier where our understanding breaks. If we could fully understand what happens inside them, we would not just solve the mystery of black holes, we would solve the mystery of reality. Consider the scale of questions tied to black holes. Does spacetime have a smallest unit? Does it stretch infinitely or discretely? Does information survive death, or can it be erased? Is time a flowing river or a geometric dimension? Can the universe create new universes? These are not questions confined to black holes. They are questions about the fundamental nature of existence. And somehow, all of them converge inside the walls of a region smaller than a star. The mystery matters because black holes illuminate the tension between our two greatest theories. General relativity, Einstein's masterpiece, describes gravity as curved spacetime, a smooth fabric shaped by mass and energy. It works perfectly on large scales, stars, galaxies, cosmic motion. It explains the horizon, the bending of light, the stability of orbits, and the existence of black holes themselves. Quantum mechanics, our other great triumph, describes the smallest scales, electrons, photons, fields. It says information cannot be destroyed. It governs the behavior of particles near the horizon and gives rise to Hawking radiation. Both theories are stunning on their own. Both are incomplete together. Inside a black hole, relativity predicts a singularity, a point of infinite density where space-time breaks. Quantum mechanics cannot accept this. It forbids infinities. It insists that space-time must retain structure. It demands information preservation. It refuses to allow a black hole to be a perfect eraser. These two principles collide. and the interior of a black hole becomes the battlefield. The reconciliation of quantum mechanics and gravity, the dream of a unified theory, depends on understanding what happens at that collision point. Every idea we explored in earlier parts, the photon sphere, the information paradox, wormholes, white holes, fuzzballs, quantum bounces, arises from this single clash. Black holes matter because they force nature to reveal her deeper rules. But the mystery reaches further still. It matters because it shapes our understanding of the universe as a whole. Without black holes, we might never confront the idea that spacetime is not continuous, that the universe might reproduce through collapse, or that horizons can store information like cosmic libraries. Without black holes, we might never glimpse the possibility that our universe began in a bounce, or that the Big Bang itself could be the interior of a larger structure. Even our understanding of cosmic evolution depends on them. Supermassive black holes shape galaxies. They anchor galactic centers, influence star formation, and regulate the flow of matter across cosmic scales. Without them, the universe would look very different. Yet all these roles, the astrophysical and the cosmological, are only part of why black holes matter. The deeper reason is philosophical. Black holes challenge our sense of place. They challenge our definitions of beginnings and endings. They force us to ask what it means for something to exist when it cannot be observed, or to fall when space itself is the thing doing the moving. They ask us to consider whether reality has edges. When you contemplate the interior of a black hole, you are contemplating the boundary between what can be known and what must be imagined. You are standing at the edge of the universe's most guarded truths, and in that quiet, contemplative position, the mystery becomes personal. What are the limits of our ability to understand? How far can the human mind stretch to grasp structures so alien that they defy intuition? What lies beyond the end of geometry? What happens at the edge of time? These questions resonate because they mirror our own boundaries, our own limits, our own desire to know what lies beyond the horizon of our experience. There is also a practical reason this mystery matters. The technologies and mathematical tools forged in the effort to understand black holes ripple outward into other fields. Quantum information theory, holography, gravitational wave astronomy, numerical relativity, these areas were born from the black hole puzzle. They shape everything from encryption to cosmology to the way we model the universe's earliest moments. Every time we ask a question about black holes, we invent new ways to understand reality. The effort expands our knowledge even if the answers remain hidden. But perhaps the deepest reason of all is this. Black holes reveal that the universe is still full of wonder. After centuries of scientific progress, we sometimes imagine we are closing in on understanding everything. Then, we see a black hole, a region where basic concepts dissolve, and realize how much remains unexplored. The mystery matters because it humbles us. It reminds us that the cosmos is not small or simple. It reminds us that the world is not finished offering surprises. And it reminds us that the greatest discoveries often lie in the places where our understanding breaks down. As you drift in this quiet reflection at the crossroads of physics, geometry, and awe, a final question forms gently like a ripple on still water. If black holes reveal the limits of our knowledge, then what does it mean that we can imagine what lies beyond them at all? In the quiet after a long journey like this, it's hard not to feel a kind of softness settle in. We've drifted from the edge of a black hole to its deepest mysteries, through horizons and photon spheres, through the strange bending of time, and into the possibilities of new universes branching from the darkness. And yet, as the story comes to rest, the mystery feels even larger than when we began. Black holes remind us that the universe still keeps secrets, not because it wants to hide them, but because the laws that shape everything, from the stars above you to the breath in your chest, are deeper than we can see from the surface. They bend, they shift, they fold in ways that ask us to slow down, to wonder, to let go of certainty for a moment and simply observe. The horizon is not a wall. It is a question. The interior is not a place, it is a possibility. What lies beyond may be nothing at all, or everything. Whatever the truth is, it holds something gentle too. It holds the reminder that mystery is not a barrier. It's an invitation. An invitation to keep asking, to keep imagining, to keep listening to the quiet places where the universe speaks in its softest voice. And as you rest now, you don't need to carry any of the complexity with you. Let the equations fade. Let the spirals of spacetime settle back into stillness. Let the last traces of curvature smooth out like a calm sea returning to peace. All that matters is this: you are here, safe, warm, floating in the softest corner of the cosmos. The universe is vast, but tonight it is gentle. Thank you truly for taking this quiet journey. If this story brought you even a moment of calm or helped you drift a little closer to rest, I'm deeply grateful you're here. Now, ease into whatever comes next. Sleep, reflection, stillness. The stars will keep their silent watch, and the mysteries we've explored will wait patiently for whenever you're ready to return. Good night, and may the calm of the cosmos stay with you.